When solving our equations, we want to be aware of kind of two special cases that can come through. One special case would lead to the fact that there are no solutions for that equation. So what we would do is we would write no solutions, and this comes through in a specific way. We're going to look at two examples here and see how this shows up in the solving. We could just write no solutions. That's typically what we'll do. There is a symbol used. You might see this symbol, a circle with a line through it, that kind of represents this empty set of possible solutions, meaning there's nothing in there. The other case is going to be infinitely many solutions, so where absolutely anything can be a solution. So you can see it written like this. You could also see the phrasing, x is all real numbers. So real numbers is any number that you can plot on a number line. So we were just saying x is all real numbers. In terms of symbolically, something you might see, it more shows up later in calculus classes, but just in case you run into it, how we would write this is x, and then the symbol for belongs to, and then real numbers is given with an R that has an extra line on it. So this is just actually, that symbol right there reads as x is all real numbers, or x belongs to the all real numbers set. So just in case you see those symbols, but I'm going to go ahead and write it out in words each time, which is perfectly fine. So let's see how these two special cases come through. So let's get some practice with our solving linear equations. So I'm going to do simplify both sides of the equation. So on the left-hand side, it's all simplified, so there's not much to do there. On the right-hand side, I have this x plus x, which is 2x. And then I have this plus 8 minus 6, which is a positive 2. Now, at this point, we could say infinitely many solutions, because what we could see is we have the same exact thing on both sides of the equation, which is great. Most often we take this a step further of going through our steps and solving equations of kind of moving our variable term. So to do that, it would be difficult to choose because they're exactly the same, but the idea is that I would be subtracting 2x from both sides of the equation. And what that means is x is going to disappear. It's going to completely wipe out from our equation, and all we'll be left with is this statement 2 equals 2. So all we have left are constants. We don't see our variable anymore. But what's key is that when we have this statement involving our constants, it's a true statement. And when it ends up being a true statement, that leads to the conclusion of infinitely many solutions. So that means we could go through and choose absolutely anything for x and plug it in, and it will balance on both sides of the equation. So infinitely many solutions happens when you're solving, and either you get the completely same expression on both sides of the equation, or as you go through and solving for your variable ends up disappearing. Then look at the statement between the two constants. If it's a true statement, then we have infinitely many solutions. Let's look at what happens with this case. So 2x plus 2 on the left-hand side, and we'll have 2x, and then 9 minus 6 is a positive 3. Now we could see here, at least having that comparison in the previous example, would be that now it doesn't balance. We can see our 2x values, but our constants are different. So we go this extra step of subtracting 2x from both sides, which means our variable disappears. So that tells me we're going to have a special case solution. So we'll have a constant of 2 is equal to constant of 3. Now 2 equals 3 is a false statement. That does not balance. And this leads to the conclusion that there are no solutions. Nothing will work for x to balance that equation. So those are special cases when you're solving. If your variable disappears, then you need to evaluate whether you're getting a true or false statement out. If it's true, infinitely many solutions. If it's false, no solutions.